So for the two co-hosts, you can now have a look at the Zoom window on your computer. There should be two red dots there indicating that we are recording. So if that goes wrong, let me know. So we can restart the recording. Therefore, afterwards, everybody can have something to review. Okay, so anyway, let us start. I will share my screen. Can you see my screen?
Yes.
Which screen can you see? That is the problem.
We can see the full, like, desktop.
The full screen is what I can see.
Full screen, like EXP.
Okay, let me reshare it. Sorry about that. Oh, should be this one. Okay, that's good. Okay, now let's start. First, let us have a very quick review of where we are. Okay, we start this semester by asking what is machine learning and when it would be a good idea to adopt machine learning for some real world tasks. So in the first session, we end up understanding machine learning as software 2.0, and we want a computer to program itself. Well, that is very good. Self-programmed computer. And with three conditions. It needs data. So from the data, it can learn experiences. It has experience, and it can learn something from the experience. And it needs a task that could be possibly performed reasonably well from the experience. That means we need to believe that there are some patterns to be discovered from the data, and the patterns would help us for future performing of the task. And thirdly, which is basically a feasibility issue, patterns, that we probably do not want explicit math of the problem of the task. If we do have explicit math or physics about what we want to model, we just apply that model and code and program the computer by ourselves. Okay. So following our discussion in the second session, we start asking and understanding how to achieve this goal, which sounds too good to be true. Let the computer to learn by itself. Well, we have taken home the points that in the basic form, which is our focus of study in this basic foundations of the machine learning, there are 4 elements that makes the framework using which we can let the computer to learn from experience. The first one is, of course, the experience itself, which is the data. Okay. And we understand that the data, this notion, comes with 2 layers. In the basic layer, this refers to the black box mechanism, the black box physical processes which underlies, which generates the data in the background. We don't have direct observation. We cannot directly assess this knowledge. What we can assess is a set of samples from the data, x1, y1, x2, y2, and you note that in our settings, we split the data into two parts, x and y. The x part refers to the information that has been and will be available to us, which means it is always available. And that means that in a narrow sense refers to data. And the second part of the data, well, this data is a broad sense, which means all the historical records. It's a piece of information that is our interest. We know the answers to the X in the historical data, but we do not know the answers. And if we want our model to produce such kind of answers for the Y part, which is called target. So data and target. Okay, these are called data samples. And very often they also call data points. And very shortly, we will explain why we call them points. And with the data, we need to delimitate, we need to constrain ourselves the range in which we would like to consider the hypothesis. The hypothesis that describes the relationship from X to Y. And the reminder here is, please understand this notion more like a limiting factor. It is more like to prevent you from using something that is wildly designed to describe the data, rather than an enabling, an empowering factor. It is, of course, it is something that allows us to model data, but what I want to emphasize is here, please try to understand it. The main point here is to prevent us from using anything and limit ourselves using only the things that has been prescribed in this set. Okay. And if you remember our Excel table, I myself have acted as the selection mechanism and manually selected some hypotheses from this set. And we try to find one that suits our flower data samples in the last lecture. So here is a selection mechanism. Of course, we want the selection to be performed automatically rather than manually. And fourth, we have a loss factor here. We call that loss. We call that objective function. We call that cost. Call that errors, risk. There are a lot of names, but it boils down to the basic notion that you need some criteria to evaluate how well or how poor your hypothesis have performed on data. So that is where we are in this subject. Okay, according to our roadmap, after this, remember the why, what, to, how. In the third part, we will start learning our first machine learning model, which is perception. Yeah, that model comes very naturally if you recall what we have been doing in the last week. We have manually changed the parameters that determines a line splitting a two-dimensional data space that hopefully gives us good split of class 1 and class 2, or class 0 and class 1, I don't remember. Anyway, the two classes of the flower samples. And today's topic is how to formalize this natural design and make our first classifier. And arguably, it is also the first artificial intelligence classifier. Well, we'll come to this point a little bit later. Okay.
Hey, June.
Gitas, you?
Yeah, I'm here since last 5 to 7 minutes.
Oh, that's good.
Just waiting for
Finally,
you
you're
to
here.
complete.
Can you raise your hand? Yeah. I make you the
Yeah.
co-host, and we thank to other students who were here on your stand.
Yeah,
Okay,
I was just in a meeting with a lecturer. So.
it's fine.
Yeah.
Yeah. Okay. I hope everything is clear here. If you have, I won't throw a polling right now. If you have questions before we go, you can type it in the chat box.
Do you want me to set the quiz deadlines or anything, or did you complete that?
Sorry?
Discussed last time. Do you want me to set the quiz deadlines?
No.
Or you done that?
I forgot to mention that the quiz because we need to cope with people may have difficulties in arranging time. So I set a grace time for the first few quizzes. We are not very strict on deadlines. So for quiz 3 and quiz 4, still everybody can complete the quizzes before the corresponding Saturdays of the week. That is the setup. From quiz 5, we will set up deadlines for the quizzes. Okay, because on the fourth week we will have everybody have to determine whether to quit or continue a subject. So before that, we allow everybody to a very long time to attempt the quizzes. Well, okay, where are we? Yeah, good. The design of the model is actually exceptionally basic. I can, let me try a pencil. So yes, this is a review, and this is to introduce the model. I will quickly introduce the structure of the model, and then I will give you a very intuitive impression of how the model, which means the model family, can lead us. Well, here, okay, my iPad. I need to share my iPad with my daughter who is perform homeschooling. So, and let me look. This needs some time to synchronize. So I will just use my mouse to write things bear with me for a moment. When the synchronize finished, we will be able to write things more properly. Okay, it's here. Okay, sure. In the you must have seen a lot of graphic representation of perceptions. Usually, people would draw the chart of the model like this. Okay, I just draw it here. You have something. What? Okay. Okay. You have something as the node to represent the attributes of the data. And we then, for each data sample, look, you could have many nodes to represent the data, and the number of nodes is equals to the number of attributes in your data. So here in our example, we just use 2. We then give each attribute a corresponding coefficient. That's W1, W2, and we take the sum. The sum. This is the sigma for sum. For the pairwise production, we then arrive one number, and this one number represents the information we collected from the data. So however complicated structure, however rich information has been carried in the data sample, we summarize everything, use one number. Okay, so this is a point to keep in mind. And this is a little bit counterintuitive. When I learned machine learning, sometimes I was in doubt. Well, how could you even attempt to encode such rich information of the data distribution using one number? Because this practice is very popular in a lot of machine learning models, not restricted to linear model or perception. But it turns out that basically we are defining a function on the data space, and we can look into very rich family of functions, which means this is usually adequate or sufficient for the applications. Now we have one number representing one data sample. And the next step is to do something about the number. Okay. Up to here, this is the practice that is essentially done in every linear models. And after that, what to do with the number, the weighted sum of the data attributes, that is particular to perception. Okay. And the decision making is very simple as well. Well, you set up a threshold. Let's call that theta, or very often people call that B as well. And for a reason which will become clear very soon, I will just call that W0. This is just a name, so nominal. It doesn't carry any information. Anyway, we need a threshold. Okay, and the output function looks like that. So basically, if this is the number produced by summing up all the x and w, which means x1 times w1 plus x2 times w2, and you check the range of this number, you still have some threshold. And on this side of threshold, we just output one value. And on this side of threshold, we output another value. So what is on the threshold, basically that it usually does not matter, because we are considering a continuous space. It's very, very rarely. And to the probability of 0 to be precise, we will need to deal with the value on the threshold. So we consider it's on one side of the threshold and on the other side of the threshold. We produce two values. And the two values represent the classes of the sample. Okay. Given the table of the data and the two parameters, you remember this, right? In our Excel spreadsheet, we have the data attributes in two columns. We have our W1 and W2. Well, not arranged in exactly in this way, but you remember that are in two cells. The take-home points here, remember, this guy corresponds to the entire column. So you can consider if you flip the X table down, make X1 here, X2 here. So this is one data sample or a flower. This is another data sample of flower. So those guys are now in a line, waiting to be fed into the processing pipeline of the model. So this line moves this way. Every single guy comes in, put the X1 into this node, the X2 into this node, and to be processed by exactly the same pair of W1 and W2. So the W does not change with the sample of X. W specifies the model, right? And after the information has been processed and the number is calculated, you arrive into this decision-making step, and the model gives a positive or negative, or well, A or B or 0 or 1 or whatever classification decision. Okay. Are we clear now? In the last week, I called for some volunteers to join me in the hand-on practice. So I got 2 people emailed me. Maybe I missed some message. Sorry about that. But I have 3 bookings, but I have only 2 people emailed me, and I replied them to let them to register on a web service called CodeCock. Just here. It's called codecock.com. So if you are one of the people, you can now log into your CodeCock account. And in the next, we will do some hands-on practice together. I will copy the invitation token to the chat box of Zoom. You can use the invitation token to join in the project. Because we only have a few volunteers, so I think everybody who are interested in to come up and let us practice the coding together, you can join. It is called Cocalc, COCALC.com. I got some questions. I will address those questions very soon. Okay, let me copy the token first. Where is my token? Oh dear, autocorrect does not allow me to type. COCALC. Cocalc project. So basically, this is a platform very similar to Colab. The only convenience it provides us is it allows collaborators to work together on a same block of code. So I can help you, especially if you are not a very skillful coder, I can help you. And hopefully for the other people, you can learn from how people get trials and error and learn something. Okay, here. If you log into your Cocalc account, if you log into your Cocalc account, I think the Zoom window is really a deal breaker. I cannot see my menus. When you log in, this is what you will be located when you log in, and here will be a box that allows you to enter the project invitation, and you enter this here, you will be guided to the project we are in. Okay. So where are we? I got a few requests of help. So for the threshold value, that strikes me to the point that I have to see. You have asked a very good question that I do not have a quick answer. The threshold value basically determines where is the boundary. But of course, you will see, wow, Jin, you are talking nonsense. We have all the parameters determines where is the boundary. So imagine that the threshold determines how the boundary moves parallelly in this way, and the other parameters determines the rotation. But of course, you need to keep in mind we are talking about not only in two-dimensional space. This model applies to multi-dimensional space, and in which case the classification boundary is in a sense more than the English word boundary. In English word boundary, you think about a one-dimensional loop or something that encloses some area within, but that boundary we were talking about is like a hyperdimension, hyperplane thing, which is just an object in a multi-dimensional space. And that object has one less dimension than the space it lives in. Like in a two-dimensional space, the boundary is a one-dimensional thing. In the three-dimensional space, the boundary is a two-dimensional thing, like a surface or a plane, so on and so forth. So it cut the space into half, and the threshold determines where is the boundary. And I will come up with a slightly more illustration, intuitive illustration of the concept. Well, in the following discussion of this and the next week, we will remove the boundary. Well, in our discussions, we do not need that concept. It is just in the back of our head, but we don't include this concept in our discussion. And fortunately, you will find that all the math still works without this troublesome notion. Okay, hopefully some people have joined in. Yeah, we got some people. Look, hi, William Fong, Nguyen Ting Dan, Atvit. Okay, thank you very much for coming. This is a notebook, and you can see. I will invite you to perform programming later. Okay, so yeah. Don't mess up with my code, please. Here we prepare the data. And what I'm doing here is that I further simplify the problem a little bit, very little bit. What I'm doing? Well, we have a range of x1. So the data lives in this range of x1, and we have a range of x2. Okay. I then discretized x1 and x2 into 50 bins. Now, actually, I have simplified things. Previously, the value can take continuous. The value of the x attribute can take continuous values in this range. But now I have split them into 50 locations, and it has to choose one of the location to get itself in. So basically, I now have an array of 50 by 50 equals 2,500 dots. Our data samples are a subset of those dots. Why I'm doing this? Well, it will become clear very shortly. So let me run my code here. Now you can see. So one color represents one class of data, flower, and the other color represents the other class, and those gray dots represent where we do not have an observation of the flower class. So now we understand data. And in the next, what I'm going to do is I'm going to do a very, how to say that, brutal thing. I will come up with a hypothesis. Before I'm talking about this, consider what a hypothesis is. What a hypothesis is in this data space. In this data space of in this data space of two data sets of 2,500 possible samples. Those are the possibilities. So what is one hypothesis on this? Okay. One hypothesis would be like this. Here is 0. Here the class is 0. Here's the class is 0. Here's the class is 1. Here's the class is 1. Maybe here's the class is 0. Here's the class is 1. Here's the class is 0. So on and so forth. Okay. And ask yourself a question before we go. How many possible hypotheses in the entire hypothesis space? So how many possible hypotheses if our task is to color each of the dots in one color or the other? Okay, if we have one dot, how many hypotheses? 2, right? It could be 0, it could be 1. If we have 2 dots, how many hypotheses? 4. Okay, 0, 0, 0, 1, 1, 0, 1, 1. If we have 3 hypotheses, 8 possibilities. So it could be 0, 0, 0, 0, 0, 1, 0. Okay, you get the point. If we have 4, we have 16 hypotheses possible. And now, just for fun, let's compute 2 to the power of 2,500. How many hypotheses of the entire possibility? Any one of you, the people who are coding together with me, you can now freely run this and show us the number. Can you? Oh, good. We have this number of hypotheses to choose from. Okay. And I have a quick question. Look, now, actually, not all those hypotheses are good ones, obviously. If we define good or bad purely based on whether the hypothesis, whether our coloring agrees with the data we have observed, okay? And now we have observed, have a look, the length of Y sample, 132 dots. It's 132 because 132. So it should be less than 100 because I have only plotted the points that belongs to class 0 and class 1. So this. Oh, give me a sec. Yeah. Okay, sorry. It gives you the indexes where the Y is class 1 or class okay, where it's a class 1 or class 0. So I take niche and take the length, so which is 82. Now we have 82 dots that has already been colored for us. Then from the 2,500 possibilities, freedom of choices, we remove the 82 locations. Well, this is actually a great reduce, because for each dot removed, we need to half of the possibilities, right? Because now for all the possibilities with this colored wrongly, we remove it, we eliminate it. And even with this, how many possibilities we are left? This many. What we were talking about is like, okay, if we are considering coloring 3 possible data, we consider 8 possibilities. But if now I tell you your coloring must agree with your observation, and you have observed that at this point, the class is class 1. So you only have the freedom of classing or choosing colors for the unobserved samples here, which gives you 4 possibilities. So that is why here is a reduce of the power. Okay, and in the next, I just choose one of well, this many trillions, zillions, gazillions, gazillion possibilities, and draw them out. So here is one of such hypotheses. This is one of such hypotheses, which means I fixed the color at wherever I have observed the color. So you can carefully check all the coloring in this figure agrees completely 100% with the colors here. There is not a single violation. Okay. But would you call this coloring anything useful? How much confidence do you have when it comes, for example, to here, where we have not observed a sample? So we have the freedom to color it in whatever way. I use this 50 by 50 grid because I want to generate such a random coloring for you. I need to fix where I need to generate the random colors. Therefore, I have this setting, by the way. So I think we can all agree that you have very little confidence that this coloring here, this classification here, has anything to do with the information that is carried in the data. Basically, this looks very random. That does not look contains much information at all. That practice corresponding to the wrong practice we mentioned here. Remember that we mentioned the hypothesis family is basically a limiting factor. It limits the possibilities. You can potentially try to describe the relationship in the data. If you do not have any limitation, you just freely describe the relationship in whatever way you want, only observing one rule that your description needs to agree with the observation, then this is one of the things you are likely to get. So for now, I think we are very well motivated to introduce some limiting factor, which is the linear family here. So I show you, this is a hypothesis produced by one member of a linear family. Okay. And the mechanism is like this. It's exactly as we have introduced in our introduction to the data structure, to the model structure. Yeah. So get the linear decisions. And here we assume X is a table. Okay, a table has a shape, and the shape is the rows times the columns. Example, for example, at temp, so it has 3 rows and 4 columns. And if you print, it 3 by 4. And the shape itself is a, you can call that an array, does not harm here. It has 2 elements. And the first element refers to the number of rows, which is, of course, the number of samples. And corresponding to this interpretation, if you flip the table 90 degrees, not flip, rotate it 90 degrees and let those samples one by one getting in line to get into the processing pipeline. And here n, the 3 is n, or the number of rows, or the number of samples here. Okay. So this is how many samples is in the line to be processed. And the linear decisions is another array in Python. I just use a quick construction of arrays in Python. In Python, you can construct an array like that. So this is an array of 1, 2, 3, and more than that, you can construct an array out of another array. So this we have agreed that, for example, this is array 1 to be 1, 2, 3, and I want to construct an array 2, and array 2 is something constructed from the elements in array 1. For example, we can use like A times 3 for A in array 1. And let us see what is array 2 is. You'll probably be able to guess it. Okay. The construction looks a little bit strange at first, but when you get used to it, it's very convenient. So we have the X grid, our X grid. Maybe one of the people, whoever is here, can you let us know what is the shape of X grid? Just in this. Yeah, thank you, Vika. Okay, you can start with X grid itself. Follow me. I'm above you. You can follow me. Put here, Vika or somebody. Okay, you can follow me here. No, this is my cell. Okay, this belongs to me. Yeah. Whoever wants to follow us, you can follow us. We do this together. Yes, that's good. And you can execute that to know its shape. You will find a large number, perhaps. You execute that. Oh dear, that is a little bit embarrassing. So this is a grid. Let me have a look. Why I have that, you do not have. Let me execute yours. Oh, now it works. So it is a large one. Okay, let's play with the first few of X grid. Maybe the first 10 elements or 5 elements, because we have a lot of people here. So let's save our screen space. The 5 elements in X grid. Okay, let's do a for loop in the 5 elements, perhaps. We just print it out and see what do we have. Where's my wrong? Okay, 1 by 1. It prints out an element in the X grid, right? Okay, I then would invite you to take out the elements in each of the rows in X grid, which means you can do this: x1, x2 equals x. In Python, when x itself has 2 elements, and you take x1 and x2, you basically take the 2 elements. You can type like this to show the difference. See, this is my result. I think you need an x1 here. Okay, good. Now, what the point here is now we know that we can take the elements of each data sample that is in a data table and do something above the data sample, right? So we do not need this x here anymore. We can just write x1 and x2 here. So we remove that, and you can run the code and to assure yourself this is still okay. Okay, And then, because now we have the x1 and x2, we can do the computation here, right? We can allocate W1 and W2 and multiply that with x1 and x2 and take the result. See, for example, just for well, an awkward thing here, I need to distinguish W1 to be W1, my W1, I call W1 gene, okay, to be 0.5, W2 gene to be 1.2 maybe. So I then compute x1 times W1 gene plus x2 times W2 gene here. Well, I let A to be this. I'll call A gene to, because when I'm executing here, I do not want to mess up your result. So here, I maybe take one thing like this. Okay. See, what do we have? Now, basically, you have achieved a model, right? Your model basically begins to produce the value A here. Remember our value A here. It begins to produce A here for each single input, correct? Okay, congratulations if you have a right here. Yeah, and from here, we can then remove the print thing. We give it just a comment out. And remember our construction of the very awkward but well, fancy Pythonic construction of an array. So for each element, and by element, I mean the data sample in the table, I will produce a value. Then I can just copy what I want to produce before the for and embrace of the entire thing, includes the entire thing into a pair of brackets. I do that again. Here is where we were. I cut copy the entire thing before the for, and then use a bracket, pair of brackets to include it. Now, let's call that is a result GL. Okay, and I print result GL. Perhaps it would be a good idea to keep maybe a reference of something here to check. Oh, embarrassing. No, we do not need this. We do not need this assignment here. So remove that. Okay, 4.5 noise, 4.63. Everything looks perfect. Well, congratulations. Without considering the threshold, we almost have done the majority of the computation of a perception model using Python. Okay. Given a table of data, now you can remove the subset taking part. Previously I took that because otherwise it will be working on on 2,000 more samples, and the screen space is simply insufficient. Now, because you have already debugged, test how the code works, you can remove that tiny little small subset thing and apply the model to the entire data set. So that is one perception model half done in one line of code. Okay, which is not bad at all. Considering the original implementation of the perception model in this way. I think that's Frank Rosenblatt implementing that back in 1960s. Okay, appreciating the elegance of Python implementation and get the thing settle in your mind. We relaunch the poll and see how things go. This time you can I give you maybe 4 minutes. You can play with the code. And let me change the earphone. The session is too long just. Okay. Yeah, my my headset went flat at the right moment. So let me have a look at the chat board if you have any questions. Where is that? So, wow. Okay, I got a question about what part of the coding. Okay, the coding, Microsoft, maybe for, yeah, the example just shows to calculate a linear combination of the data attributes. So I'm sure a lot of you have used the 9 in the previous subject. And in the 9, you have the perception model. The perception model, when you try to explain it, it would be in model repository or node repository, something like that, a tab on the left part of the screen. To use it, you just drag that node into your workflow. And our code here, the code here just demonstrates, the code here demonstrates what happens when you drag the node and the node appears in the workflow. Okay. So to implement the threshold itself, the implementation of the threshold itself is quite straightforward. Well, you just need to add an if statement about the value produced by the weighted sum. It, for example, like return 0 if it's or return -1 if it is less than 0, or return +1 if it is greater than 0. Traditionally, in the literature of perception, people are used to use the -1 and -1 and +1 for the two classes. So if you want to implement that using Python, it's pretty straightforward. I'll show you. For a string of numbers, such as, if you just copy this, okay. No, what? This is just to want to make things a little bit easier to understand. So I copied the result of the previous computation. I still add this. Okay. I can do things for this. Okay, this is again an array. So I can, for values in this array, I would like to return +1 if v greater than, for example, 5.6, sorry, 4.6. Otherwise, -1. So basically, this means decision, that decision, okay, we write down
the if statement this way. Else. Okay. This statement can be simplified as if +1 same, and we can further put this into here. And it becomes another well, array. But basically, this is just a demonstration of how to implement how the theoretical computational steps translate to software implementation. And in practice, we usually do this with the help of libraries, which therefore, instead of storing the X, consider that as an array, and we need to loop through each row of the table, we can consider that as a data matrix, and the W as a parameter matrix. And the computation of these translate to this way. I hope you still get some memory about the linear algebra. But if you do not, here is a very quick reminder. So when you have X in such a way, and this is the first data attributes, attribute 1, attribute 2. Okay, maybe A is not a good number. We just write that down, like X1, X2, XK. So you have K attributes per sample. Okay. And you have n samples. This is the table. So someone please try to type in the chat box. If you have K attributes per sample, how many coefficients in of W? Any thought about that? No, not 2 to the time of K. Yeah, K. So like if you have 2 attributes as in this way, so for each attribute, you need 1 W. If you have maybe another attribute, you add another W. You have the same number of attributes and the coefficients. So you have W1, W2, WK. I hope we have some knowledge, some familiarity with the matrix vector multiplication. That is a matrix times vector. So don't be scared. This is just a convenient way of arranging the computations. It's nothing more than the element-wise production and take the sum. So basically, if you have k elements, k attributes in each of data sample, and we need to combine these data attributes with k coefficients. So imagine you have a for loop. It goes this way in the data table, and it goes this way in the coefficients. So for one go, you produce one number here. This is A for the sample for the first sample. For the second go, you go through the same set of parameters. Remember that? We use the same set of parameters for all the data samples. You have the second go, and this contributes to the number A for the second sample. You go all the way. At last, you go through this row, and you have A of the last sample. The entire thing is handled by NumPy or whatever, like PyTorch or TensorFlow. All those linear algebra computation libraries can handle this computation pretty easily. For fun, and which is also a very useful tool in doing such engineering or research, you have the website called Matrix Calculus, produced by some people. Okay, so call that X, and you can choose X is a matrix. Can you see clearly? Because those math sample does not go very well when I enlarge it. If you can see it, I just keep the font size as is. If it's too small, let me know, okay? You can choose X is a matrix. Okay. X times W, and you let W a vector, and it will automatically recognize that X will be a matrix and W will be a column vector, a vector in this way. So then it can help you to calculate the X and W's computation, and which is more the derivative of the result with respect to either X or W. For example, like with respect to W. Well, we need to we come back to this issue later when we talk about neural networks. But for now, we do not need the derivative. We don't need about this. We do not need this part. We just purely compute this. Okay. Now, this very good web service can help us generate Python code. You click Python. Now, Python downloaded. So actually, it performs all the like check and exception handling for you, and also the derivative. So basically, we do not need that much. What we do need is just to compute f and g. This actually we do not need the g. We just need f. So let me change that. This is f, x, and w. So it do the check, like it need to assure x is a NumPy array, and x has 2 dimensions, which means this is a matrix rather than some like a multi-dimensional tensor or one-dimensional vector thing. I just do the brutal force stuff. I remove all this. We just keep the function value, and we do not need a gradient. So basically, the very basic stuff is this. Okay, you can copy this into any notebook, and it will work. X dot W. Okay. So, for example, we just keep the essential part, and I call that x, my x, w, my w. So what I'm going to do is I will let my x GL to be none other than my experimental data here. So before that, I print that out for you. Okay, a 2-dimensional table, and the WGL. I just take the 0.5 and 1.2 here. But I need to wrap it into a NumPy array. Okay, although look, although this is printed in a horizontal way, but keep in mind, this is a one-dimensional vector. This is a vector. This basically does not have the second dimension. This is just one string of numbers. It is different from the x. X has 2 dimensions. Okay, so the result is an array of this. I hope at this point you are a little bit familiar with this string of numbers. This is equaling to this. Well, back to our point. Now we achieved. We start from considering limiting our choices of coloring the doors. And we decided that maybe it would be a good idea to limit ourselves to make decisions according to one number, and that number will be produced by only using, where is my notebook? By only using one coefficient upon each data attribute. So this is the number. And we will base our decision about the color, the class of that sample solely, purely on this number. Okay, and we discussed how to implement this if we take the values in the data organized as a table. We do a for loop over all the rows in the table and constructed another array that contains the result of computing this number for the data table. And then we introduce a quick way computationally, I mean, theoretically, it's not quick, but engineeringly, it's quicker for a computer to do the, if you tell the computer now you are doing a regular matrix and the vector multiplication thing, we take a more efficient implementation of the algorithm. Okay, so we realize that the perceptron is a very elegant model. The essence of the computation is none other than it's just to combine each data sample with a group of coefficients, and those coefficients apply to each of the data attributes. And the implementation is extremely simple. By having the data, look, this is actually a simplification. We do not need this. In the implementation, usually the data is given. We have the x. We just use the numpy dot product between the data and a set of parameters. Okay. So this is the number upon which, based on which we will decide the class. Maybe we can see the prediction. Note that I didn't take the effort to transform the judgment into numbers, but this is not difficult to do. You have the false and truth stuff here. Well, I just keep it in this way, so you know that this is a result of classification. It does not have numerical meaning or significance. A more formal implementation of the model is given in our notebook here. Where is my notebook? Here. The class notebook in week 3 and week 4. Here is the week 3 one. Now I think we are comfortable to read this implementation. This is one example of a perceptron model. You can consider that this is one candidate in the candidate set. Okay. So there is an implementation like that. We take 2 possible candidates into consideration. Okay, now our hypothesis is extremely narrow. We only have 2 candidates. We need to select one of it. And in the training part, I don't think I want to explain statement by statement here. If you are interested, you can come and ask me in the QA sessions. But basically what it's doing here is to compare the output of these 2 or any of the hypotheses in the set. By hypothesis, I mean the function, and the function just implement what we have implemented just now. So we take each of such functions and apply the function to each of the data sample given in the training, and we take a record of whether the output sample agrees with the desired answer. If it agrees with desired answer, we mark it as an accurate classification. Otherwise, it is inaccurate. So after processing all the data, the hypothesis will have a score. And we do this for each of the hypotheses. At the end, we take all the scores and select the best performing hypothesis. And that is basically what training does. Okay. So how do we go right now? Where's my podium? Okay, I can see many people want to think about it for a while. Okay, as usual, I will lead everybody through the quiz. And after the quiz, I think the time is about to have our Q&A session. If you have other commitment after the class and you have questions, you can leave the question in the chat board. I try to address that first. And if you have time, stay with us. Maybe we can freely interact and address your questions in the Q&A time. Give me a sec. Let me see some coffee. I have an excellent question. As before, I'm always happy when I have kind of stimulate, or sorry, I kind of encourage this question at this point. I read the question. It is the W here, the coefficients are the parameters machine will generate automatically and pair with X to see which set of W have the most accurate result. Exactly. Your guess, your hypothesis, I mean hypothesis, is accurate. That is what machine learning does. And this is in the next step what we will do. We have discussed our hypothesis structure. The structure basically is this: okay, there is one coefficient for each data attributes, and very naturally in the next step is okay, now you have the hypothesis family, you have the structure. Then how do you search in the structure to find the one particular set tuple of a group of coefficients or weights, so much so that this group of weights produce nice agreement with the observed data. So this is the question we will address in the next lecture, and hopefully we can have a discussion about why we believe this is a good idea. So anyway, this is good question. Okay. Where is our quiz? Interesting. So as usual, in the student mode, the quiz will give you marks after the quiz is over. So don't worry about that. It will give you the highest marks in several attempts. But for now, stay with me. Okay. Again, the order of the answers differs from one user to another. Don't copy my screen choices. Understand the question and the answer, please. Question 1. How many parameters in the linear regression model? Okay, embarrassing. I haven't mentioned regression model. Basically, it's very similar to the perception model, only that the target prediction is not a class, it's a number itself. So I didn't mention that it's because it's basically simpler than the perception. So at this point, without doing anything, you just produce this number. So that is a linear regression model. Okay. Taking the input of 10 data attributes, and the model has been trained based on 150,000 training samples. So the question is, how many parameters in this model? The answer is 11. So those two answers are traps. Those are wrong. The correct answer is 11. You have 10 data attributes. I don't know why this always comes out. Ah, dear. And each data attribute corresponds to a coefficient. So 10 attributes will need 10 coefficients, and those coefficients belongs to the model parameter set. And remember here, there is another input that is in the perception is called threshold. In the regression model, it's called a bias, which means that is a constant that you add to each data sample without a corresponding input x value. So basically, the computation of the linear model takes in this form. X1, no, X1 W1 plus X2 W2 plus dot 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 plus xk wk plus b. I said in the beginning of this lecture, the b sometimes is called w0, sometimes it's called theta, so on and so forth. So we have 11 parameters governing the model that has produced 150,000 training samples. Okay. Question 2. Consider the value a equals w0 plus wx1, w2x2 computed on some two-dimensional sample x equals x1 and x2 and two widths x1 and x2 and the constant offset bias maybe w0. And let w represent the four set of parameters. This w1, w0, w1, w2. Okay. Now we represent the function a as a function of x and w. Basically, it says in this function, here we input x, input two attributes x, and in that representation, it requires you input w0, w1, because because of the notion thing. Here we start from 1, but here we start from 0. So let me just input maybe let's call that w99. Okay, this corresponding to this w0. So it's just the name of the parameter. It asks, is this function linear? A function is linear to something means we always call that linear thing, linear thing, linear thing. And you have seen that when you apply the function to the data space, it cuts a straight line, and you think, well, a line is linear. Okay, that imagination is roughly correct, but mathematically speaking, a linear thing is for one object is here and the other object maybe here, and see if this object is on two-dimensional space. If you produce a value for this object and produce another value for this object, then if you draw a line from this object to another object, that means the mechanism or the function producing values for this thing along the line. So at each point along the line, if you apply f as well, it will produce a new value. And the linear means along that line, you will also produce a value which is a straight line. And that is called linear. A counterexample, which means a nonlinear example, would be like that. If you produce a value here, oh, why I cannot change the? Okay, there's two denotations. If you produce a value here and produce another value here, but in between, you produce another value here, another value here, another value here. Basically, on that line, it's the function corresponding to this way. This is not a linear function. So the question asks, consider the two mathematical objects, W and X. And it asks you whether A is linear, whether A is producing lines, given lines of X and W. This question is a bit confusing. The answer is that AW is linear with respect to W. Please be reminded that when you write it in this format, W0, W1, X1, W2, X2, it is not linear with respect to X. Why? Because in this format, you have a constant here. This constant does not change if you change X. So if you go through a line in the X, the value of A is not strictly linear along the line. So the correct answer is it is linear with respect to W, but not to X. We will come to this point in the next lecture when we introduce a geometric view. When we introduce a geometric view of the model, it will become more clear. So where's my quiz? This is an interesting question. I give you some time to think about it. If someone have figured it out, you can support the answer in the chat box. I give you 5 minutes on this. Basically, it asks, okay, if I want to classify the samples into two classes, the red circle and the blue triangle, using perception. For A, B, C, and D, on which cases I would be completely successful, and on which cases that is impossible for me to be completely successful. An idea? Okay, let me have a look. Yeah, we start to achieve some consensus, because basically perception is cut a line in the X space. So for this, easy. I don't think we have any doubt about this, right? This example tries to deceive you, like into thinking this line is not working. But if you look into that beyond the deception, it's easy to discover, okay, this line is not working, but maybe this line is working. And for this guy, have this line. But for this guy, there is no line on the plane that could be separate the samples into two classes arranged in such a way, right? Cut this, maybe not right. This way, this way, this way, whichever way you cut, we end up with two different classes of samples end up on one side of the line. This is a non-separable case. So the answer is A, B, and C. Okay, so let me submit that. Okay, to summarize, first question, 11 parameters. Second question, linear, the function in this way is linear with respect to the parameters, not with respect to the input, the data attributes. Third, 1, 2, 3, A, B, and C are linearly separable cases, while this is not linear separable. I have a suggestion that can we draw a curly line? Think about this term, a curly line. I would rather call that a curve, right? Yeah, so but that is a good suggestion. The suggestion is a very nice one that people thought that, okay, look, you have struck a connection that has a deeper, it's a deeper connection, links question 3 and question 2. Remember that we have discussed the model, the linear model is linear with respect to the parameters, but not necessarily with respect to the data attributes. So keeping the linearity with the parameters untouched, but we can somehow transform the way we represent data. So how about not respect data using x1 and x2 only? We can add up new attributes, such as add up new attributes, but without creating new information. How to do that? For example, we can have x1, x2, and the third attributes, we just repeat x1. We use x1 to the square. And the third one, we can use the square of x2. So we do not introduce any new information, but we create auxiliary axis on which, if we cut straight in those maybe subspaces, the effective cutting in the original space becomes curly. So that is the idea behind a lot of more powerful data models, which we will study later in this semester. Yeah, that is right. Another interpretation is the change of the coordinate system. Exactly, yeah. I like that interpretation. So yeah, basically we come to a conclusion today. We discussed our first machine learning model today. It's a construction of the model of perception. Perception adopts a particular specification of the hypothesis space, which means that in plain English, it is the conclusion about the data sample So the relationship from X to Y is determined by one value. That value is the weighted sum of the data attributes. So for whichever number of attributes in the data, I will allocate the same number of coefficients and arrive a weighted sum. And I do something about the sum, which is comparing it with a threshold. Or alternatively, you can consider that would be subtract the threshold from the result and compare that with 0. The same thing. So we have this decision-making process, and that is called perception. And then we explore how to implement perception using Python code. And then we explore how to utilize some modeling help assistance so that it can automatically generate the Python code and help us to call the linear algebra libraries to compute that using matrix vector multiplication. Okay, with this we conclude our discussion about perception model, the construction of perception model, and which leads to the next discussion of how to choose a set of weights that makes the model's behavior agrees with the observed data. Okay. So thank you very much for attending. If you don't have more questions, you can leave freely. If you have questions, you are free to ask me. I have a question from Xinxin Huang. So far, we are up to linear model, but perception is more than that, like the curve. Well, we are, how? Well, I don't think I can explain that clearly in English because that basically refers to math. Perception is a model. If you apply that to the plane, the raw input data, that will cut a straight line in the data space. And that is not a curve, that's a straight line. However, perception belongs to the linear model family, not in the sense that the boundary must be linear with respect to the data, but in the sense that the model result is linear with respect to the model parameters. So for the data part, you are free to transform the data. Therefore, using the same model structure, you will end up with a curly boundary in the raw data space. Let me try to give you an analogy. See, if you are a bank manager, you probably perhaps you want to find the profitable customers and those risky customers, and you collect the data like the customer's income and how much debt they are in. And you find that if you cut a straight line in the customer profile space, where each dot represents a customer and one coordinate of the dot represents the income of the customer, the other coordinate represents how much debt the customer has. If you cut straight line, maybe you find I really do not like that because either way, I'm unsatisfied because historically shows maybe this cluster of customer is good one, are good ones, were good ones. They pay back their loans on time and gives us profit, and that may be a little bit riskier. But the boundary is not straight line. So basically, I think I described the situation you want to deal with. Then, if you stick to the perception model, and if you stick to the customer income and the debt, the original form, basically you do not have much to do. You have to cut a straight line somewhere. So you are facing the decision of either throw away some profitable customer or bring in some risk. On the other hand, you are clever. You think, okay, how about if we this is just for example, boost the customer income with a nonlinear factor. For example, we can take the square of the customer income into consideration. So therefore, now if we take the square of the customer income, my decision boundary will be determined by something like A times the square of the income plus B times the times income plus C times the customer's debt. And then this will describe a nonlinear landscape on the terrain of the income and the debt. So if you use this newly computed value, you can end up with a curly classification boundary. Okay. I show you. Where are we? This, okay. Take a look. Now, let me write it here. Okay. And of course, I can write it in this way. So I move this to that part. I keep the 0 here. This does not change anything, correct? Okay. What I'm going to do right now is, for example, maybe put another parameter here. What I'm going to do, okay. So for W, if you are one can choose W, the situation doesn't change to you. You do not have the knowledge that, okay, this guy is just a repetition of this guy. You do not know that. You just process 4 numbers, 3 numbers, as if you process a data set has 3 attributes. This is a designed feature of the data. Let's do this. So this still belongs to the linear model family. Okay, it seems that I have blown away the everything. I try this maybe. Okay. Slowly bring things back. It still looks a bit well straight. Hopefully you can distinguish the difference. Let me make it more obvious. Okay. I think it's because I'm striking to a more street part of the landscape. Let me think about that. That doesn't change the. I have a suggestion that how about change x times. So you mean this? Okay. This is just to add a possibility of this. Okay. So let me. Change the show data part. Oh, Ctrl F or Ctrl. Let me Google that. Ctrl F. Yeah, Ctrl F, right. So, yes. I don't think I need a function to do that. I can just copy it here. So, where is that? I just put it here, and I'm computing the A here. Then you can appreciate the change of the value. Okay. Uh-oh. Should be agreed. So this is the landscape produced by the produced by that set of parameters. You can see that this it's changing, but not completely linearly. Look, this line slopes in this way, but here this line slopes in this way. So which means the direction of the lines gradually changes. I perhaps this is not so intuitive an interpretation. Let's
Hi, June. Sorry. This is Xingxu here. So I just wonder why there are several colors in this graph here.
the colors.
Yeah. Since
Okay.
we only have two classifications, right?
Okay, look, I have removed the judgment here.
Oh,
I draw this A value according to the color. I draw the A value according to the color. I
Yes.
didn't make the decision. So the decision making is something like that. Okay, I now decide a color here. So the area that has a darker coloring than my threshold, you belong
Yes.
to color. You belong to class 0 and not a class positive or negative, and the others belong to color positive or negative, things like that.
oh, so the color here is not referring to the classification.
It's referring to the value based on which you do classification.
Sorry, I didn't get that.
So, like now the color itself, it does not matter too much. Let's call that this is yellowish. This is purplish. Okay.
Okay.
Then the classification in this case becomes to boils down to determine a color for whatever location that is colored more yellowish than the determined color, that will belong to the positive class. And for whatever that is more purplish than the predetermined color.
Yes. Okay.
So that is the way. So the determination is one thing, but the model actually produces a landscape of colors. And you can also consider the color as a height. A height means it's this way. What?
All the RGB stuffs.
So maybe you can consider this color is a lower landscape and this color is a higher landscape. So this will become something like this.
Oh, okay.
Okay.
Yeah.
And the classification becomes, okay, now I have determined a height. Maybe this is the height I would see. Below this height belongs to one class. Above that height belongs to another class. Therefore, that height will corresponding to, when it projected to the data space, will corresponding to a curly line on data space. So that is what what we mean, that you can probably produce nonlinear classification boundaries using the same kind of construction. Okay.
Okay.
Let me try using this one. I'm very unhappy with the intuitiveness of what what I have produced, but I hope you get the point.
Yeah, June, I appreciate for that. But just now you mentioned that the constructions. So this the A here, this constructions, you just change it the x1 squared. Previously it just 1 x1, but now it is x1 squared. So this is the change of the construction.
Oh, this is a change of the representation of the data. The construction solve is like that. So, okay. What I mean is you have the structure of your model like that.
Yes.
Take the sum here. This is what is referred to when I said construction. And for the x, for example, if you have, let's call this, maybe this is 100, okay? You have x1 to x100 here, okay? And you are unhappy with what you get from here. So maybe you can consider, look, I take this guy. I take a x1 square and I add a node here. I give it to here. So I didn't change my construction here. What I'm changing is
the input of the data.
yeah.
Okay, thank you so much.
Okay, let me do maybe a crazy thing. Take the sign of that. See what we have. Okay, now we have something that is really crazy. Maybe.
Oh, not bad. Good.
So yeah, it can create a very rich family of classification boundaries. It's a very interesting family.
Thank you so much, June. I will try it after the class, see how it goes.
Yeah, but no need. We will come back to this point at towards I think the end of the semester when we introduce neural networks. That is a systematic way of hugely extend this line of thought.
Oh, so maybe now I just take my steps one by one towards that.
Yeah.
Okay, thanks a lot. It's more clear to me now.
Okay. You can freely ask me questions, or you can maybe register on Kucock. Coding, sorry, I have a question. Do we still have coding exercise tomorrow? What? If you book, you come. But I'm not sure. Luo Hui Yun, can you elaborate what do you mean by coding exercise? Tomorrow is Thursday. We have a QA session by book. You can book a time slot.
Oh, hi, June. Yeah. So it's the announcement you put to register CodeHouse. So I've sent you email and book a time, I guess. So I'm not sure if.
Okay. I think you. Okay, you misunderstood. Okay. It's just my lazy. I put the volunteer booking together with the consultation booking tomorrow.
Right.
They are different things. So, but anyway, if you want to come, you come tomorrow. I have allocated 1 hour to help people. So it's just because this is not supported by ETS. This is I spent my own money out of pocket to buy a service. on this website. So the capacity is limited. If we have something like 100 more people, if you all come in, that will blow the little machine up. So I want some more, motivated student to join.
Okay, got it. Thank you.
Okay. The recording, I usually, after the session, I will quickly put a recording draft like this. Modules and online materials. So I will quickly put a draft download before anything else. And you have the password, something like that. So if you're happy, you can just take download. And it's not every week we have slides. Sometimes, for example, in this week, I do the revisions on notebooks, things like that. We do not have a slide, but I've put the recording quite quickly here. And in the weekend, we'll have time. Our TA have time. They will put the thing on YouTube, and you can view on YouTube there. I think okay, I will ask them to do, because another TA will also put a recording on Bilibili. I know some people now stuck outside Australia have difficulty to use YouTube, but you have access to Bilibili, and you can view the recording there. Basically you can, but it's not guaranteed. For example, if I have half an hour booked, another half an hour not booked, maybe I have other commitments. So, but anyway, I have no objection if you just jump in. So, do we have more questions? If no more questions, I think we can wrap up here. Well, yeah, and GitHub will hold another session. If you have other questions, maybe after you have been trying this thing out a little bit, you will find, okay, I'm stuck somewhere. You are very welcome to come back to let GitHub help you out. Okay, then yeah, thank you everyone. Thank you especially GitHub for coming. Okay, bye-bye.
No problem. Have a good day, everyone. Bye-bye.
Bye-bye.
Thanks, Joe. Bye.
Bye.
Thank you all.